Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 28, 2026, just 3 days ago. It investigates the popular Muon optimizer and finds that, despite its impressive training speed, it lacks the simplicity bias inherent in traditional methods, like stochastic gradient descent, which can lead to models failing to learn shared structures. The paper is titled, "To Use or Not to Use Muon, How Simplicity Bias in Optimizers Matters." And as we'll see later, the implications for how we choose optimizers for complex tasks are quite significant. To visualize this theoretical difference, Figure 1 compares the learning dynamics of standard gradient descent on the left against spectral GD, which serves as a simplified proxy for Muon, on the right. Focusing on the blue curves for gradient descent, the bottom left plot reveals a stepwise pattern, where the model learns the first principal component completely before starting the second one. This sequential process creates a distinct plateau in the loss curve above it, demonstrating how standard descent prioritizes dominant features one by one. Conversely, the green curves on the right show that spectral GD learns all components simultaneously, meaning the singular values rise together and the loss drops rapidly without any intermediate pauses. Moving to the practical consequences, Figure 2 applies these dynamics to a routing task. Panel A illustrates the network setup, which aims to map inputs to the target vectors shown in Panel B. The results for SGD in Panel C show clear success. The model correctly predicts patterns, even for the unboxed pairs it never saw during training. Conversely, Panel D reveals that spectral GD fails on unseen data, outputting noise outside the green training boxes, because it memorized specific examples instead of learning the rule. Panel E tracks the loss, confirming that spectral GD converges faster but misses the underlying shared structure. While Figure 3 demonstrates how Muon handles spurious correlations using menace digits modified with a cheat pixel, shown in Panel A. In Panel C, the solid green line tracks Muon's accuracy on clean data. It peaks early, and then collapses as the model overfits to the cheat pixel, whereas the blue stochastic gradient descent line stays robust. Finally, Panel D shows that while stochastic gradient descent resists weak shortcuts better, its simplicity bias can backfire if the spurious Q becomes dominant, causing it to crash harder than Muon at high intensities. So, Figure 5 highlights a quirk in the convergence stability of spectral GD. These plots track a singular value over time across 3 different learning rates. Ideally, the green trajectory should settle flat onto the red target line once the feature is learned. Instead, it oscillates persistently. This happens because the orthogonalization step amplifies even tiny residual noise, forcing the model to keep taking significant steps. As the bottom panel shows, increasing the learning rate just makes these fluctuations more violent. Alright, Figure 4 expands on the learning dynamics by testing higher dimensional cases. Panel A covers 2 dimensions, while Panel B on the right moves to 3. Focusing on the blue gradient flow graphs in Panel B, you can clearly see the saddle-to-saddle behavior. The loss curve drops in distinct steps, because, as the bottom plot shows, the model learns the 3 singular values strictly one by one. Conversely, the green spectral GD graphs show all components rising together, explaining why Muon is faster but less selective. Well, Figure 6 investigates whether adding momentum stabilizes the oscillations we saw in Figure 5. This experiment brings the theoretical spectral GD model closer to the actual Muon optimizer by incorporating momentum into the update rule. Across the 3 panels, which show increasing learning rates from top to bottom, the green trajectories continue to fluctuate around the red target line instead of settling. The bottom graph particularly highlights that, even with momentum, high learning rates drive chaotic instability, suggesting these fluctuations are intrinsic to the orthogonalization process itself. Wrapping up, 2 takeaways stand out. While Muon offers incredible speed, its lack of simplicity bias can hurt generalization on tasks requiring shared structure or robustness to shortcuts. It forces us to rethink optimizer choice not just as a speed dial, but as a fundamental architectural decision. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.